Okay, so in this next one, we have the set of integers and some three binary operations have been defined on it. We have to decide whether each one of them is commutative. So the first two you can see are clearly commutative. For any two integers a and b, we have a star b equal to ab plus 1 and that is equal to ba plus 1, because this is ordinary multiplication of the integers a and b, which we know is commutative. So that's why the first binary operation is commutative. Just like that, the second one is also commutative. For any integers a and b, we have a star b equal to, this one is a plus b plus ab. Now this thing can also be written as b plus a plus ba, using elementary properties of addition and multiplication of integers, and that is by our definition of the binary operation b star a. Number 3, we should actually write after this one line that hence the operation star is commutative, which I am not writing. You can clearly see what the cases are. Note that the third one, however, will not be commutative. To see that it is not commutative, only one counter example is enough. One example that shows that a star b and b star a are two different integers. However, to show commutativity, we have to prove it for all pairs of integers a and b. So in these first two parts, we are doing it generally, and here we will show one counter example. Note that 2 star 1, in this one the definition is this, that is a star b is the first element, 2 star 1 is 2, that is not equal to 1, which is 1 star 2. Let's just write for this one, hence this is not commutative. We should also write similar things in the other two parts, that they are commutative. Then exercise 30. For each part of the preceding exercise, are the operations associative? That is, does the, okay, no, that is the next one. Do we have A star B star C equal to A star B star C for all A, B and C belonging to the set of integers. So the same operations that we have here. The first one gives us AB plus 1, the next one A plus B plus AB, and the third one is A. So let's remember that and write the solution. Commutativity was, you could see it easily even before doing any calculation. Associative law, however, is somewhat more complicated simply because it involves three things, three elements, A, B and C. Note that, so B, you can understand because we have taken one particular example. We are guessing that it is not commutative. Let us see what happens. So first if we calculate, so the first operation is what? A star B is AB plus 1. We multiply the two numbers and add 1 to them. So 2 times 2 is 4, 4 plus 1 is 5. So just like that, 3 times 5 is 15, 15 plus 1 is 16. But if we on the other hand calculate this, then 2 times 3 is 6, 6 plus 1 is 7, 14 plus 1 is 15. That is this is not equal to this. Thus, this operation is not associative. So that is part 1. What about part 2? In part 2 we have A plus B plus AB. This one we will see it will be associative. Let A, B and C. So that's why we are taking general integers. Then A star B star C. First we calculate this one. If you want, you can calculate this outer product also, keeping A star B as it is, and then you calculate A star B. It's up to you. So we first decide to do this one. Then star C. So that is what, just like we have to add the two numbers and their product. So here we have to add these two and their product. This number, this integer plus C plus their product. So that gives us what? a plus b plus c plus ab plus ac plus bc plus abc. Do you see that there is a symmetry in this expression, in the sense that as far as the terms are concerned, among these three, A, B and C, you can in fact interchange any two of these. For example, in this expression you want to write C in place of A and A in place of C, then the expression ultimately will not change. That kind of symmetry. And if one calculates the other one, A star B star C, so because of that symmetry, this will also turn out to be the same integer. So this will be A star B plus C plus BC, and that is A plus B plus C plus BC plus A times B plus C plus BC. And this ultimately becomes what? We have A plus B plus C. So let's write them first. And then we have AB from here, and also AC and BC. AB plus AC plus BC, and one more term, ABC. So they are the same thing. Hence, that is this operation is associative. And the third one, although the third one is slightly strange in the sense that you see, when we the binary operations with which we are familiar, they usually use both the elements. For example, when you take the ordinary sum of 1 and 2, both of them are used, and you see you get 3. Like that, when you take the ordinary product of 1 and 2, you get 2. 2, you see, you may ask this question, okay, how do you know that 2 is being used here? Because we don't see any formula that involves 1 and 2. Yes, that is a valid question, but the statement that 2 is being used here is in this sense, that if you change this number 2, the result itself changes. So that means the second number has an effect. Or for example here, although we don't see any explicit formula, but if I change this number, the result changes. So definitely the fact that the result has changed must have come from the fact that we have changed the second number. So that means the second number is affecting the sum It is somehow involved in the sum. However, in this third binary operation, that is not the case at all. It is simply just the first number. But in spite of this, despite having this somewhat strange nature, it will also turn out to be associative. We will see how. Let A, B and C be integers. Then see, by the definition of star, A star B is just A. And again by the definition of star, this is also A. Whereas if we calculate the other product, then this one is the first one, that is B, but this again is A. That is hence the operation is associative. So that's the solution. Then exercise 31 for parts 1 and 2. From exercise 229, that means our original binary operations from the first one. Decide if star has an identity. An identity element, that is does there exist an element E in the set of integers such that A star E and E star A are both equal to A. So we don't have to say anything about this third operation, only parts 1 and 2. Note that if for an integer a we have but I should also mention about e. So let us start the solution like this instead. Suppose there exists an element e such that a star e and e star a both equal a for all integers a. Then we know the definition of the operation star. So a star e means ae plus 1. E star a is also ae plus 1 because that is ea plus 1. The operation star in this case is commutative. So we don't get anything new from these two things, we get the same thing, and that is equal to a. Or, okay, then what do we get if we manipulate the equation a little bit? We get this. This implies, note that a and e are both integers, and a in fact here is any integer, e is some integer, but still after all whatever they are integers. So you look at this equation. This equation tells us what? That the product of two integers is -1, and that is possible only when one of them is 1 and the other is -1. That is the only possibility. There is no other possibility. This implies that a is equal to 1 and e minus 1 is equal to -1, or a is equal to -1 and e minus 1 is equal to 1. But we are saying that this condition is true for all a, for all integers a. So it becomes wrong when you take an a that is neither 1 nor -1. Thus, if a is, for example, 2, we have a or in fact no, the contradiction is not conditional. We already have obtained a contradiction because our statement is for all a, and here we have found only two values of a. So instead we should write like this. This is a contradiction because or it's a contradiction to our supposition. Yeah, that much is sufficient. That a can take any integer value. So our supposition is wrong. That is, there is no such element E, and hence there is no identity. So star has no identity, or there is no identity with respect to the binary operation star. Then we come to the second one. In this case, there is an identity. Note that for all integers a star 0, which is equal to 0 star a, that is equal to a. Hence 0 is an identity. And how are we excuse me, how are we getting this? A star 0, we already know, we have seen that this second operation is also commutative, so it's enough to only see a star 0. So a star 0 is a plus 0 plus a times 0. This is the ordinary product of the integers a and 0, and this is definitely a, so that's how we are getting this. So 0 acts as an identity. We have been asked to find one identity. We are not concerned about whether 0 is the only identity or not. We don't need to know about those things. The solution asks only if there is one identity or not. So this completes the solution. And there is one more. Define a binary operation star on the set of rational numbers Q via this formula. A star B this time is a plus b minus ab. Find an identity E. that is, we already know what an identity is. What's the point of again writing it? Find a rational number E such that this for all rational numbers A. Ink is needed. So that means there is some identity, we have to find it. That's the first job. Then decide which elements of the power has come back. Which element of the set of rational numbers have inverses? That is, determine for which rational numbers B there exists a C belonging to Q such that B, okay, B star C is equal to C star B is equal to E. So let us first see what our set is. The set is the set of rational numbers, and this is our binary operation. Okay, now we are in search of an inverse, and that inverse would be just like before. 0 is an inverse. Note that A star 0 is equal to 0 star A is equal to A for all rational numbers A. We can see that easily from here. A star 0, for example, is A plus 0 minus 0. or if you calculate 0 star a, 0 plus a minus 0. Star incidentally is also commutative. Hence, is an inverse. So, for this inverse, we have to calculate. So what the hell am I saying? 0 is not an inverse, 0 is an identity. So for this identity, we have to calculate inverses of those elements that have inverses. But one more question arises here. What if some other identity exists? What will then happen? Let us see if some other identity can actually exist. Although we don't really need that in this solution, but still, equal to A. If E is our identity, then A star E is this, that should be equal to A, and this should be true for all rational numbers A. And that gives us what? These two, after cancelling them, you get for all A. That condition is there, okay. Now clearly for all A, 1 minus A cannot be equal to 0, and A is also allowed to be rational. So the only possibility is E equal to 0. So this is the only identity. One can in fact find out this identity in this way. Okay. Now, next we have to find those rational numbers that have inverses with respect to this identity. Let P be a rational number for which there exists a rational number C such that P star C equal to C star B equal to our identity, that is 0. Then P plus C minus BC equal to 0. If we calculate C plus C star B, we will get this same thing. Or, okay, so we want to decide what B possibly can be. So what we can write from here is this, or what I want to say, what I want to conclude from here is that B is not equal to 1. Okay, B is not equal to 1. Yes. Okay. Note that P is not equal to 1, as otherwise, so if B is 1, in the other case, What do we get from here? Or because these two will cancel, we will get 1 equal to 0, which is clearly not true. So that is why b cannot be 1. So from this we conclude immediately that the rational number 1 does not have an inverse, and then we have to see whether the other rational numbers that are not 1, whether they can have inverses, and it turns out that all of them have inverses. Now for b not equal to 1 in, or because we have taken here a rational number b which has an inverse, that's how we have taken b, that is we assumed that b has an inverse, and then our consequence is that b cannot be equal to 1. Now we have to take something else. Now our rational number is not b, it is something else, say d. To make sure that we are taking any d, we mention that also. For any d not equal to 1 in Q, we have, so what will happen if we consider this rational number? D divided by d minus 1. Note that now this is also a rational number. D is a rational number, and because it is not equal to 1, the denominator here is non-zero. So the quotient d divided by d minus 1 is again a rational number, such that now we calculate this. By the definition of star, oh, this is minus, I should not forget that. D times this, so d square divided by d minus 1. So if we take d minus 1 LCM, then we get plus d minus d square, and that becomes d square minus d plus d minus d square. So you can see that this becomes 0. Similarly, star d is also equal to 0, and 0 is our identity. Hence, every rational number except 1 has an inverse, and if that rational number is d, its inverse is d divided by d minus 1. So this completes the solution, and it also completes this very small set of 4 exercises. So we will see in the next Friday, next Saturday. Of course, we don't have Lee. We have Galilean's algebra. The Saturday after that, we have again Lee's algebra exercises. So that will be all in this video. If you want to say something about this, you can write in the comment section below, or you can mail me here at this address. So that will be all. So see you tomorrow with our usual analysis video. Until then, have fun with mathematics. This is me, Lucifer, from a mathematical room. Have a nice night.